In this video, I want to talk about electromagnetic radiation versus nuclear radiation. And they sound similar, but they're not the same. So first, let's focus on nuclear radiation. So we know these atoms are made out of protons, neutrons, and electrons. So we know that. However, in order for an atom to be stable, it must have the correct ratio of neutrons to protons. And there's always an optimal ratio of neutrons and protons that will yield a stable atom. And here's a graph that shows what these stable ratios are. For example, maybe we have an element like zinc, which has 30 protons. So if an atom has 30 protons, it must have roughly around 35 neutrons in order for it to have a stable ratio. And we can see this belt represents the stable ratios. And let's do another example. Maybe tin has 50 protons. So if an atom has 50 protons, we can see that it should have roughly, it looks like 67 neutrons to have a stable ratio. So we see that optimal ratio depends on how many protons we have. So let's do an example. Let's say we have an atom that has 10 protons and 10 neutrons. Well, we see if we have 10 protons, then we should have roughly around 10 neutrons. So this would be a stable ratio. However, what if we have a different atom, and maybe this atom has 9 protons and 11 neutrons? Well, if we have 9 protons, then we see we should have roughly around 9 neutrons. So therefore, if we have 11 neutrons, this is unstable. This is not a stable ratio. So therefore, this is not a stable atom. So what is this atom going to do? Well, essentially what this atom does is it emits some of this nuclear radiation. So whenever an atom has an unstable ratio of neutrons to protons, it'll emit this nuclear radiation. And when it emits this nuclear radiation, this ratio changes into a more stable ratio. So for example, this atom, we see it has an unstable ratio. So it will emit this nuclear radiation. And there are lots of different types of nuclear radiation. But maybe it emits a negative beta particle. So when it emits this nuclear radiation, essentially what happens is a neutron is converted into a proton. So again, the point is this atom has an unstable ratio of protons to neutrons, so therefore it emits nuclear radiation, and when it emits that nuclear radiation, a neutron is converted into a proton. So if a neutron is converted into a proton, we have a new ratio, and now we have a more stable ratio. So again, all atoms must have a stable ratio of neutrons to protons, and if it doesn't have a stable ratio, it'll emit nuclear radiation. And again, there are different types of nuclear radiation, and each type of nuclear radiation has a different effect on how it impacts the neutron to proton ratio. For example, let's say we have this atom, and let's say this atom has the wrong ratio of protons to neutrons. It can release an alpha particle, which is a type of nuclear radiation. And when we release these alpha particles, this alpha particle takes with it some neutrons and protons. So therefore we emit these alpha particles, so we emit these neutrons and protons, so therefore this ratio will change and it'll fix into a more stable ratio. Another example is maybe we have this element, this atom, that has too many neutrons. So maybe it has too many neutrons, so it doesn't have a stable ratio. So essentially this will emit another type of another type of nuclear radiation. Maybe it will emit these negative beta particles. So when it releases these negative beta particles, it essentially loses a neutron and it gains a proton. A neutron is converted into a proton. So therefore, this type of radiation turns a neutron into a proton, and that's a way to fix the ratio. And maybe another example is maybe this element has too many protons, so it has an unstable ratio. So when we have too many protons, we would essentially emit a positive beta particle, which is again another type of nuclear radiation. And when we emit a positive beta particle, we lose a proton and we gain a neutron. So a proton is converted into a neutron. So again, the point is there are lots of different ways we can fix these ratios. If we have too many neutrons, we can release a negative beta particle and a neutron will be converted into a proton. If we have too many protons, we can emit a positive beta particle and convert a proton into a neutron. So there are lots of different ways to fix these unstable ratios. And again, the point of this nuclear radiation is all elements must have a stable ratio of neutrons to protons. And if it doesn't have a stable ratio of neutrons to protons, it can emit nuclear radiation. And there are different types of nuclear radiation, and each type of nuclear radiation has a different impact on the way it affects the neutron to proton ratio. So now let's talk about electromagnetic radiation. And there are lots of different types of electromagnetic radiation. For example, there are radio waves, which is one type of electromagnetic radiation. We also have microwaves, which is another type. And we can have visible light, which is another type, or maybe X-rays. So we officially have 7 types of electromagnetic radiation. So let's talk about electromagnetic radiation. So a common example we see in our day-to-day life is this visible light. This visible light is a type of electromagnetic radiation, like we just explained. So what is this electromagnetic radiation? Well, essentially, it's a wave. It's a wave. It has this repeating wave-like characteristic. And this wave is made out of these electric fields, this oscillating electric field. And what is an electric field? Well, if we have a strong electric field pointing in this direction, then if we were to add a positively charged particle, it would feel a strong force in this direction. However, if we have a weak electric field pointing in this direction, then if we threw a positive charged particle here, it would feel a weak force going in this direction. But the point is, these electric fields are invisible electric fields that exert forces on charges. So again, this electromagnetic radiation is essentially just a wave of this oscillating electric field. So we have this electromagnetic radiation, this visible light. So therefore, if we quickly threw in a positive charged particle right here, it would feel a strong force in this direction. So that's what this electromagnetic radiation is. And again, something important to realize is whenever we have with this electromagnetic radiation, whenever we have a strong electric field, we always will have a perpendicular magnetic field. And if we have a strong electric field pointing in this direction, then we'll have a strong perpendicular magnetic field pointing in this direction. If we have a weak electric field pointing in this direction, then we will have a weak magnetic field perpendicular. So this electromagnetic radiation is made out of these electric fields and these magnetic fields, these oscillating electric and magnetic fields. But I'm just going to focus on the electric field component. And again, we also know that this is a wave, so we have this oscillating electric field. So therefore, we have a wavelength. We'll have a wavelength. And whenever we have an electromagnetic radiation wave that has a wavelength in the range of 400 to 700 nanometers, then that by definition is visible light. So by definition, visible light has a wavelength in this particular range. So therefore, we know this is visible light. So therefore, this electromagnetic radiation would have a wavelength in this particular range, because that, by definition, is what visible light is. However, maybe we can have an X-ray. So an X-ray machine will emit these X-rays, which is, again, another type of electromagnetic radiation. However, by definition, an X-ray will have a wavelength in this range. So that's by definition. That's the convention humans have chosen to define these X-rays. We can also have radio waves. So maybe we have this radio tower emitting these radio waves. And whenever we have electromagnetic radiation, because again, this radio wave is just another type of electromagnetic radiation. So whenever we have an electromagnetic wave with a wavelength that's larger than 0.1 meters, then by definition, it's a radio wave. Radio waves have these wavelengths that are 0.1 meters or larger. And what's interesting is this radio wave, this radio tower will emit lots of different radio waves. All of these different radio waves with slightly different wavelengths. But what's interesting is there is information in these radio waves. In this particular combination of radio waves with their slightly different wavelengths, there's information in this combination. So therefore, this radio is going to receive this unique combination of radio waves, and it's going to interpret it. It's been programmed to interpret this particular combination of radio waves to turn it into music. But the point is, there are lots of different types of electromagnetic radiation, and these different types are defined based on the particular wavelength, the length of this oscillating unit. So again, here is the spectrum of electromagnetic radiation. So we talked about visible light, X-rays, and these radio waves. So again, if the wavelength happens to fall in this range, it's an X-ray. If the wavelength happens to fall in this range or larger, it's a radio wave, and etc. And visible light happens to fall under this particular spectrum. So again, this is what electromagnetic radiation is. So again, if we had an electromagnetic wave, and it happens to have a wavelength of this length, this particular length, then we can see it would be an infrared wave. So this would be an infrared wave. But again, the point is there are lots of different types of electromagnetic radiation depending on what type of wave, how the length of the wavelength. And something else important to realize is we can have two different forms of electromagnetic radiation, and we see they have different wavelengths. So if this electromagnetic wave happens to have a wavelength that's this length, it by definition would be a microwave. However, if this electromagnetic radiation wave happens to have a wavelength of this length, then by definition it would be a gamma ray. And this is a little unintuitive and an abstract notion, but we can think of these electromagnetic radiation waves as waves, or we can think of them as particles. So we can think of them as particles made out of these photons. And a way you can think about it are these electromagnetic waves are essentially made out of these photons. So it's these photons that make up these electromagnetic waves. But again, these electromagnetic waves have wave-like characteristics, and they also have particle-like characteristics as these photons. But something else important to realize is the longer the wavelength, the lower the energy per photon each photon has. However, if you have a very short wavelength, we can see here this is a very short wavelength. So if we have a very short wavelength, then these photons are going to have very high energy. So again, we see this gamma ray has a very short wavelength. So if it has a very short wavelength, then therefore it would be made out of photons that are high in energy. It would be made out of these high energy photons. So this is just something you just need to memorize. Again, this microwave had a long wavelength. So if this electromagnetic radiation has a long wavelength, then it's made out of low energy photons. And again, this is just something you just have to learn. So now we know the difference between electromagnetic radiation and nuclear radiation. And again, we know what nuclear radiation is. All elements have an optimal ratio of neutrons to protons. And if it doesn't have a stable ratio of neutrons to protons, then we know it can emit nuclear radiation. And there are different types of nuclear radiation. And each type of nuclear radiation has a different impact on the way it stabilizes this ratio. And again, we know there are lots of different types of nuclear radiation. There are alpha particles and positive beta particles and negative beta particles. However, another type of nuclear radiation are these gamma rays. So we already learned these gamma rays are a type of electromagnetic radiation. And in fact, these gamma rays are the only type of electromagnetic radiation that is also happens to be nuclear radiation. So therefore, we can have an unstable isotope. For example, this barium-137 is a particular radioactive isotope. This particular element with this particular molecular mass is essentially unstable. It has an unstable proton to neutron ratio. So therefore, we know it'll emit nuclear radiation. It'll emit nuclear radiation, and in fact, it happens to emit gamma rays, which again is the only type of electromagnetic radiation that is also nuclear radiation. So it'll emit these gamma rays. And remember, these gamma rays have these short wavelengths. So because they have these short wavelengths, they're made out of these high energy photons. So therefore, this is dangerous. This barium-137 is dangerous. It's a radioactive isotope. So therefore, it has an unstable ratio of protons to neutrons. So therefore, it releases nuclear radiation. In particular, it releases these gamma rays, which release these high-energy photons, which are really dangerous. Because if these high-energy photons hit human tissue, or any type of tissue, it'll essentially enter inside of the cell, and it'll essentially react with our DNA. And essentially, these photons have enough energy to essentially rip off electrons from our DNA. So if it rips off electrons, it can essentially damage our DNA, and when our body tries to fix that DNA, it introduces mutations, which can eventually lead to cancer. So again, these high-energy photons are very dangerous. They can essentially rip off electrons and damage biomolecules inside of our cells. So the rule of thumb is whenever we have a form of electromagnetic radiation that has a very low wavelength, usually higher than essentially 10 nanometers. But again, whenever we have this low wavelength electromagnetic radiation, we have this ionizing radiation. So all electromagnetic radiation that has these short wavelengths, so at this wavelength and shorter, is referred to as ionizing radiation. So all these types of electromagnetic radiation is made out of photons, these high energy photons, which can essentially damage biomolecules.